Okay, now we're going to question 6. Draw two more vertical line segments, FG and HJ, connecting the hypotenuse of triangle ABC with side BC. Okay, so let's go to our triangle that we drew at the very beginning. And let's make a couple more line segments on there. Okay, I'm going to make one to the left and one to the right. Okay, here's one right about here. And then here's one to the left, right about here. Okay, and it says we needed to label those FG and HJ. Okay, let's call this FG and HJ. Okay. So I've got my two new line segments. Now it says, explain how you know that triangles ABC, DEC, FGC, and HJC are all similar. Okay, well if I go back and I look at this triangle, all of these triangles have right angles down here because these are vertical lines, right? And then all of these triangles also share this angle right here. So how many angles do I need to prove similarity? I need two. Two angles and I can prove similarity. So I've got one angle and I've got a second angle in all of these other triangles. So by angle-angle similarity theorem, they're all similar. They're all the same shape. They're just getting bigger and bigger and bigger and bigger. Okay. So let's write down what we just described. Triangles ABC, DEC, FGC, and HJC are all similar by angle-angle similarity theorem because they all share a 45-degree angle and they all have a right angle. All right, so far so good. So now let's look at part B. It says measure each of the sides of the two new triangles that you created and record the side length measurements for all 4 triangles in the table. Okay, so let's go back to our triangle and let's do some measurements. And remember, you did not put your sides in exactly the same place that I did, and that's okay. You're going to put down your own measurements. So we're going to get different numbers. Okay. The number that I'm getting for side FG is 87. This is 87 millimeters. And the number that I'm getting for HJ is 45 millimeters. Okay, so let's start putting these in the table. The side opposite angle C in the big triangle, we already remember that was 102. And then in triangle DEC, that was the first small one we did, we had 65, or I had 65. The one I just measured, FG, was 87. And then for HJ, that was 45. Okay, now let's start looking at the lengths of the sides adjacent. Okay, if I'm going back to my picture, these ones here on the bottom, these are the adjacent sides. Okay, so I'm gonna erase this 65 because I don't want to get confused. Let's start with this one. This one is 45 here. Well, it should be the same as these, right? This one was 65. And then this one should be 87. It's a little bit off. Let me remeasure this one again. This one is actually 86. I was off by a little bit. Let's rewrite this as 86. And then this last one down here, we already measured it before, it's 102. Okay, so those are the sides adjacent. So I'm going to go back and fix my earlier measurement because I was off. So now in my first triangle, the big one, triangle ABC, the side adjacent was 102. And then DEC was 65. And then triangle FGC, the side adjacent was 86. And then in triangle HJC, it was 45. And now let's measure these hypotenuses. Okay, so I already know that the long one is 144, and I already know that this one is 92, so let's get these other two. Let's see, I'm getting 64 for this one. 64. And then for CF, this looks like it's about 122. Okay. So let's go back and let's put the length of the big hypotenuse was 144. And then DEC was that first triangle we drew. That one was 92. And then FGC, that was the one in the middle-ish. That was 122. And for HJC, that was 64. And remember, your numbers may look different because you drew your lines in different places. Okay? So now, these we're going to get the same answers though, because these ratios, they're all going to be the same. Right? So let's take the side opposite divided by the hypotenuse. Okay? So we're doing opposite divided by hypotenuse. So this is going to be 102 divided by 144. And we already did this earlier on the calculator, but let's go ahead and pull it back up. 102 divided by 144, 0.708. Okay, and let's just do it for all of these. Let's do it for DEC. This one is 65 divided by 92. Okay, so I got 65 divided by 92. And I got 0.7065, which rounds up to 0.707. And let's do FGC. This was going to be 86 divided by 122. So 0.705. And now the last one is 45 divided by 64. So, let's do 45 divided by 64, and I get 0.703. Okay. You may already start to be noticing a pattern, but isn't that crazy that all of these different side lengths, they're all within like 5/1000ths of each other? They're almost exactly the same. Okay, now let's look at the sides adjacent. So this one is going to be the side adjacent divided by the hypotenuse. And actually all of these are the same, right? So we can basically just copy these numbers over. We got 102 divided by 144, 0.708, 65 divided by 92, 0.707, 86 over 122, 0.705, and 45 over 64 equals 0.703. Now this only works for 45, 45, 90 right triangles. With any other triangle, you'd actually have to do different calculations because they will be different. But in this case, you know, the length of the side opposite and the length of the side adjacent, they are the same. So, and now let's do the side opposite divided by the side adjacent. So we're doing opposite divided by adjacent. And all of these numbers are the same, right? So we know we're going to get 1 for all of these answers, but let's just write it down anyway. We're going to get 102 divided by 102 equals 1. 65 divided by 65 equals 1. 86 over 86 equals 1. 45 over 45 equals 1. All right, so now we're starting to notice a pattern. We're getting the same numbers when we divide the sides, even though our triangles were similar but not congruent. They were different sizes, but our ratios stay the same. And to be honest, we already knew this because we knew that similar triangles have proportional sides, right? So let's go ahead and expand on that on the next page.